Living in Los Angeles, you cannot help but notice the air. On most days, you can see the air, but not the nearby San Gabriel Mountains. By and large, airborne particles, collectively termed atmospheric aerosol, are responsible for this view-obscuring pollution that reduces our air quality, impacts our climate, and adversely affects our health. Aerosol particles are ubiquitous in the atmosphere and originate from a wide variety of human and natural sources. For example, wildfires, desert dust, and fossil fuel combustion. These particles are small, with diameters ranging in size from a few nanometers, smaller than viruses, to tens of micrometers, about the width of human hair. Aerosol particles exert large but highly uncertain effects on Earth's climate, directly by scattering incoming sunlight back to space, and indirectly by seeding cloud formation and altering their reflectivity in lifetime. In fact, without aerosol particles, there would be no clouds in our atmosphere. As many of us have experienced during our time at Caltech, aerosol particles also adversely impact air quality and, by extension, human health. Exposure to ambient aerosol is associated with increased risk of respiratory disease and is estimated to cause up to 9 million premature deaths per year globally. Now, aerosol particles can either be directly emitted into the atmosphere from a source, termed primary aerosol, or formed in the atmosphere through oxidation of gaseous emissions, termed secondary aerosol. In Shanghai, for example, most of the urban smog arises via direct emission of aerosol particles from coal-fired power plants surrounding the city. By contrast, the smog in Los Angeles is mainly formed from oxidation of emissions from human activity. For example, uncombusted gasoline vapors and tailpipe exhaust. Similarly, the smokiness of the Great Smoky Mountains results almost entirely from the oxidation of gaseous compounds emitted from plants and trees. That said, globally, most aerosol particles are formed in the atmosphere through oxidation of organic gases, those that contain carbon, and are hence termed secondary organic aerosol, or SOA. SOA, unfortunately, is highly variable and chemically complex. Human and natural sources emit thousands of organic gases that could form SOA, and even when formed from the same precursor, differences in environmental conditions, for example, temperature, humidity, and available sunlight, impact the oxidation chemistry and result in compositionally distinct SOA. Owing to this chemical complexity, characterization of the formation, properties, and fate of SOA in the atmosphere represents a formidable challenge, leading to significant uncertainty in assessment of its environmental and health impacts. This is where my research comes in. Rather than make measurements of SOA amid the immense complexity of the real atmosphere and struggle to decouple all of the potential variables impacting its formation and properties, I studied the composition of SOA formed in a massive 24,000-liter Teflon chamber under highly controlled environmental conditions. I focus on SOA formation from the most abundantly emitted and thus important organic gas precursors, such as pinene, the compound responsible for the smell of pine trees, and investigate how the molecular composition of SOA formed from these precursors varies as a function of temperature, humidity, and other environmental factors using a suite of advanced analytical instruments. My name is Kenseth. I'm an atmospheric aerosol chemist, and in this way I pull molecules out of thick air.
Thank you. That was Christopher Kenseth.